Hi, welcome back to Easy Math with Dr. Nasir, your path to math confidence. Well, in today's lecture, we will formulate general solutions for some given linear ODEs. Well, see an exercise. Verify that the functions y1 of x is equal to exponential of minus 3x, y2x is equal to exponential of 4x, form a fundamental set of solutions for the ODE d2y by dx square minus dy by dx minus 12y is equal to 0 on R. Formulate the general solution. Well, see solution. For x belong to R, consider d2y1 by dx square of x minus dy1 by dx of x minus 12y1 of x is equal to d2 by dx square of exponential of minus 3x minus dy by dx of exponential of minus 3x minus 12 exponential of minus 3x, which is equal to d by dx of minus 3 exponential of minus 3x minus into minus 3 into exponential of minus 3x minus 12 exponential of minus 3x, which is equal to 9 exponential of minus 3x plus 3 exponential of minus 3x minus 12 exponential of minus 3x, which is equal to 0. So this shows that y1 is a solution of the ODE 1.1 on R. Now for epsilon to R, consider d2y2 by dx square of x minus dy2 by dx of x minus 12y2 of x is equal to d2 by dx square of exponential of 4x minus dy by dx of exponential of 4x minus 12 exponential of 4x, which is equal to d by dx of 4 exponential of 4x minus 4 exponential of 4x minus 12 exponential of 4x, which is equal to 16 exponential of 4x minus 4 exponential of 4x minus 12 exponential of 4x is equal to 0. So y2 is the expression of the ODE 1.1 on R. Now for epsilon to R, consider Wronskian of y1 and y2 is equal to determinant of y1, y2, derivative of y1, derivative y2. So we have determinant of exponential minus 3x, exponential 4x, minus exponential minus 3x, 4 exponential 4x, which is equal to 4 exponential x minus 3 exponential x, which is equal to exponential x, which is non-zero. So the functions y1, y2 are linearly independent on R. Thus y1, y2 form a fundamental set of solutions for the ODE 1.1 on R. So the general solution for the ODE 1.1 is y of x is equal to c1 y1 of x plus c2 y2 of x, where epsilon to R and c1, c2 are arbitrary constants. So y of x is equal to c1 exponential minus 3x plus c2 exponential 4x, where epsilon to R and c1, c2 are arbitrary constants, which is required general solution of the given second order linear ODE. Well, see another exercise. Verify that the functions y1 of x is equal to cosine hyperbolic of 2x, y2 of x is equal to sine hyperbolic of 2x, form a fundamental set of solutions for the ODE d2y by dx square minus 4y is equal to 0 on R. Formulate the general solution. Well, see solution. For epsilon to R, consider d2y1 by dx square of x minus 4y1 of x is equal to d2 by dx square of cosine hyperbolic 2x minus 4 cosine hyperbolic 2x, which is equal to d by dx of 2 sine hyperbolic 2x minus 4 cosine hyperbolic 2x, which is equal to 4 cosine hyperbolic 2x minus 4 cosine hyperbolic 2x, which is equal to 0. This shows that y1 is the expression of the ODE 1.2 on R. Now for epsilon to R, consider d2y2 by dx square of x minus 4y2 of x is equal to d2 by dx square of sine hyperbolic 2x minus 4 sine hyperbolic 2x, which is equal to d by dx of 2 cosine hyperbolic 2x minus 4 sine hyperbolic 2x, which is equal to 4 sine hyperbolic 2x minus 4 sine hyperbolic 2x, which is equal to 0. This shows that y2 is the expression of the ODE 1.2 on R. Now for epsilon to R, consider Wronskian of y1, y2 is equal to y1, y2, first derivative y1, first derivative y2, which is equal to cosine hyperbolic 2x, sine hyperbolic 2x, 2 sine hyperbolic 2x, 2 cosine hyperbolic 2x, which is equal to 2 cosine hyperbolic square of 2x minus 2 sine hyperbolic square of 2x, which is equal to 2, which is non-zero. So the functions y1, y2 are linearly independent on R. Thus y1, y2 form a fundamental set of solutions for the ODE 1.2 on R. So the general solution for the ODE 1.2 is y of x equals c1 y1 of x plus c2 y2 of x, where epsilon to r and c1 c2 are arbitrary constants. So y of x equals c1 cosine hyperbolic 2x plus c2 sine hyperbolic 2x, where epsilon to r and c1 c2 are arbitrary constants, which is required general solution of the given second order linear ODE. Well, see another exercise. Verify that the function y1 of x equal to exponential as cosine 2x, y2 x equal to exponential as sine 2x, form a fundamental set of solutions for the ODE d2y by dx square minus 2dy by dx plus 5y is equal to 0 on R. Formulate the general solution. Well, see solution. For epsilon to R, consider d2y1 by dx square of x minus 2dy1 by dx of x plus 5y1 of x is equal to d2 by dx square of exponential x cosine 2x minus 2dy by dx of exponential x cosine 2x plus 5 exponential x cosine 2x, which is equal to d by dx of exponential x into cosine 2x minus 2 sine 2x minus 2 exponential x into cosine 2x minus 2 sine 2x plus 5 exponential x into cosine 2x, which is equal to exponential x into cosine 2x minus 2 sine 2x plus exponential x into minus 2 sine 2x minus 4 cosine 2x minus 2 exponential x into cosine 2x minus 2 sine 2x plus 5 exponential x into cosine 2x. So we have d2y1 by dx square of x minus 2 dy1 by dx of x plus 5 y1 of x is equal to 0. This shows that y1 is a solution of the ODE 1.3 on R. Now for epsilon to R, consider d2y2 by dx square of x minus 2 dy2 by dx of x plus 5 by 2x is equal to d2 by dx square of exponential x into sine 2x minus 2 dy by dx of exponential x into sine 2x plus 5 exponential x into sine 2x, which is equal to d by dx of exponential x into sine 2x plus 2 cosine 2x minus 2 exponential x into sine 2x plus 2 cosine 2x plus 5 exponential x into sine 2x, which is equal to exponential x into sine 2x plus 2 cosine 2x plus 2 exponential x into cosine 2x minus 2 sine 2x minus 2 exponential x into sine 2x plus 2 cosine 2x plus 5 exponential x into sine 2x, which is equal to 0. It shows that y2 is a solution of the ODE 1.3 on R. Now for epsilon to R, consider Wronskian of y1, y2 is equal to y1, y2, first derivative y1, first derivative y2, which is equal to exponential x into cosine 2x, exponential x into sine 2x, exponential x into cosine 2x minus 2 exponential x sine 2x, exponential x sine 2x plus 2 exponential x cosine 2x. Expanding the determinant, we have exponential 2x cosine 2x into sine 2x plus 2 exponential 2x sine square of 2x minus exponential 2x cosine 2x into sine 2x plus 2 exponential 2x sine square of 2x, which is equal to 2 exponential 2x, which is non-zero. So the functions y1, y2 are linearly independent on R. Thus y1, y2 form a fundamental set of solutions for the ODE 1.3 on R. So the general solution for the ODE 1.3 is y of x is equal to c1 y1 of x plus c2 y2 of x, where epsilon to r, c1 c2 are arbitrary constants. So y of x equals c1 exponential x cosine 2x plus c2 exponential x sine 2x, where epsilon to r and c1 c2 are arbitrary constants, which is required general solution of the given second order linear ODE. Well, see another exercise. Verify that the functions y1 of x equal to exponential x by 2, y2 x is equal to x exponential x by 2, form a fundamental set of solutions for the ODE 4d2y by dx square minus 4dy by dx plus y is equal to 0 on R. Formulate the general solution. Well, see solution. For epsilon to R, consider 4d2y1 by dx square of x minus 4dy1 by dx of x plus y1 of x is equal to 4d2 by dx square of exponential x by 2 minus 4d by dx of exponential x by 2 plus exponential x by 2, which is equal to 2 divided by dx of exponential x by 2 minus 2 exponential x by 2 plus exponential x by 2, which is equal to exponential x by 2 minus 2 exponential x by 2 plus exponential x by 2, which is equal to 0. This shows that y1 is a expression of the ODE 1 by 4 on R. Now for s belong to R, consider for d2 y2 by dx square of x minus 4 dy2 by dx of x plus y2 of x is equal to 4 d2 by dx square of x exponential x by 2 minus 4 d by dx of x exponential x by 2 plus x exponential x by 2, which is equal to 4 d by dx of x by 2 exponential x by 2 plus exponential x by 2 minus 4 into x by 2 exponential x by 2 plus exponential x by 2 plus x exponential x by 2, which is equal to 4 into x by 4 exponential x by 2 plus 1 by 2 exponential x by 2 plus 1 by 2 exponential x by 2 minus 4 into x by 2 exponential x by 2 plus exponential x by 2 plus x exponential x by 2, which is equal to 0. This shows that y2 is a solution of the ODE 1 by 4 on R. Now for s belong to R, consider Wronskian of y1 y2 is equal to y1 y2 first derivative y1 first derivative y2, which is equal to exponential x by 2 x exponential x by 2, which is equal to exponential x by 2 x exponential x by 2 1 by 2 exponential x by 2 x by 2 exponential x by 2 plus exponential x by 2. Expanding this determinant, we have x by 2 exponential x plus exponential x minus x by 2 exponential x, which is equal to exponential x, which is non-zero. So the functions y1 y2 are linearly independent on R. Thus y1 y2 form a fundamental set of solutions for the ODE 1 by 4 on R. So the general solution for the ODE 1 by 4 is y of x is equal to c1 y1 of x plus c2 y2 of x, where x belongs to R, c1 c2 are arbitrary constants. So y of x is equal to c1 exponential x by 2 plus c2 x exponential x by 2, where x belongs to R, c1 c2 are arbitrary constants, which is required general solution of the given second order ODE. Well, see another exercise. Verify that the functions y1 of x is equal to x cube, y2 of x is equal to x exponent 4 form a fundamental set of solutions for the ODE x square d2y by dx square minus 6x dy by dx plus 12y is equal to 0 on open interval 0 to plus infinity. Formulate the general solution. Well, see solution. For x belong to open interval 0 to plus infinity, consider x square d2 y1 by dx square of x minus 6x dy1 by dx of x plus 12y1 of x is equal to x square d2 by dx square of x cube minus 6x d by dx of x cube plus 12x cube is equal to x square d by dx of 3x square minus 6x into 3x square plus 12x cube, which is equal to x square into 6x minus 6x into 3x square plus 12x cube, which is equal to 0. This shows that y1 is a solution of the ODE 1.5 on open interval 0 to plus infinity. Now for x belong to 0 to plus infinity open interval, consider x square d2 y2 by dx square of x minus 6x dy2 by dx of x plus 12y2 of x is equal to x square into d2 by dx square of x exponent 4 minus 6x d by dx of x exponent 4 plus 12 x exponent 4, which is equal to x square d by dx of 4x cube minus 6x into 4x cube plus 12 x exponent 4, which is equal to x square into 12x square minus 6x into 4x cube plus 12 x exponent 4, which is equal to 0. We show that y2 is a solution of the ODE 1.5 on open interval 0 to plus infinity. Also for x belong to 0 to plus infinity open interval, consider Wronskian of y1 y2 is equal to y1 y2 first derivative y1 first derivative y2, which is equal to x cube x exponent 4 3x square 4x cube, which is equal to 4x exponent 6 minus 3x exponent 6, which is equal to x exponent 6, which is non-zero. So the functions y1 y2 are linearly independent on 0 to plus 20 open interval. Thus, y1, y2 form a fundamental set of solutions for the ODE 1.5 on open interval 0 to plus 20. So the general solution for the ODE 1.5 is y equals to c1 y1 of x plus c2 y2x, where x belongs to 0 to plus 20 open interval. c1 c2 are arbitrary constants. So yx is equal to c1 x cube plus c2 x exponent 4, where x belongs to 0 to plus 20 open interval, and c1 c2 are arbitrary constants, which requires the solution of the given second order ODE. We'll see another exercise. Verify that the function y1 of x equals cosine log x, y2 x equals sine log x form a fundamental set of solutions for the ODE s squared d2y by dx square plus x dy by dx plus y is equal to 0 on open interval 0 to plus 20. Formulate the general solution. We'll see solution. For x belongs to 0 to plus infinity open interval, consider s squared d2y1 by dx square of x plus x dy1 by dx of x plus y1 of x is equal to s squared d2 by dx square of cosine of log x plus x d by dx of cosine of log x plus cosine of log x, which is equal to s squared d by dx of minus 1 by x into sine log x plus x into minus 1 by x of sine log x plus cosine log x, which is equal to s square into 1 over s square sine log x minus 1 over s square cosine log x plus x into minus 1 by x of sine log x plus cosine log x. So we have s square d2y1 by dx square of x plus x dy1 by dx of x plus y1 of x is equal to 0. This shows that y1 is a solution of the ODE 1.6 on 0 to plus 20 open interval. Now for x belongs to 0 to plus 20 open interval, consider s squared d2y2 by dx square of x plus x dy2 by dx of x plus y2x, which is equal to s squared d2 by dx square of sine of log x plus s d by dx of sine of log x plus sine of log x, which is equal to s squared d by dx of 1 over x cosine of log x plus x into 1 over x cosine of log x plus sine of log x, which is equal to s squared into minus 1 over s squared cosine of log x minus 1 over s squared sine of log x plus cosine of log x plus sine of log x, which is equal to 0. Which shows that y2 is a solution of the ODE 1.6 on 0 to plus infinity open interval. Also for x belongs to 0 to plus infinity open interval, consider Wronskian of y1 y2 is equal to y1 y2 first derivative y1 first derivative y2, which is equal to cosine of log x sine of log x minus 1 over x sine of log x 1 over x cosine of log x, which is equal to 1 over x, which is non-zero. So the functions y1 y2 are linearly independent on 0 to plus infinity open interval. Thus y1 y2 form a fundamental set of solutions for the ODE 1.6 on 0 to plus infinity open interval. So the general solution for the ODE 1.6 is y(x) equals c1 y1 of x plus c2 y2 of x, where x belongs to 0 to plus infinity open interval. c1 c2 are arbitrary constants. So y(x) equals c1 cosine of log x plus c2 sine of log x, where x belongs to 0 to plus infinity open interval. c1 c2 are arbitrary constants, which is required general solution of the given second order linear ODE. We'll see another exercise. Verify that the function y1 of x is equal to x, y2 of x is equal to x exponent minus 2, y3 of x is equal to x exponent minus 2 into log x form a fundamental set of solutions of the ODE x cubed d3y by dx cubed plus 6x squared d2y by dx squared plus 4x dy by dx minus 4y is equal to 0 on 0 to plus infinity open interval. Formulate the general solution. We'll see solution. For x belongs to 0 to plus infinity open interval, consider x d3y1 by dx cube of x plus 6x squared d2y1 by dx square of x plus 4x dy1 by dx of x minus 4y1 of x is equal to s cube d3 by dx cube of x plus 6x squared d2 by dx square of x plus 4x d by dx of x minus 4x, which is equal to s cube d2 by dx square of 1 plus 6x squared d by dx of 1 plus 4x minus 4x, which is equal to s cube d by dx of 0 plus 6x squared into 0 plus 4x minus 4x. So we have s cube d3y1 by ds cube of x plus 6s squared d2y1 by ds square of x plus 4s dy1 by dx of x minus 4y1 of x is equal to 0. We show that y1 is a expression of the ODE 1.7 on 0 to plus infinity open interval. Now for epsilon to 0 to plus infinity open interval, consider s cube d3y2 by ds cube of x plus 6s squared d2y2 by ds square of x plus 4s dy2 by dx of x minus 4y2 of x, which is equal to x cube d3 by ds cube of x epsilon minus 2 plus 6s squared into d2 by ds square of x epsilon minus 2 plus 4s into d by dx of x epsilon minus 2 minus 4x epsilon minus 2, which is equal to s cube into d2 by ds square of minus 2x epsilon minus 3 plus 6x squared into d by dx of minus 2x epsilon minus 3 plus 4x into minus 2x epsilon minus 3 minus 4x epsilon minus 2, which is equal to s cube d by dx of 6x epsilon minus 4 plus 6x squared into 6x epsilon minus 4 minus 8x epsilon minus 2 minus 4x epsilon minus 2, which is equal to minus 24x epsilon minus 2 plus 36x epsilon minus 2 minus 8x epsilon minus 2 minus 4x epsilon minus 2, which is equal to 0. We show that y2 is a expression of the ODE 1.7 on 0 to plus infinity open interval. Also for epsilon to 0 to plus infinity open interval, consider s cube d3 y3 by ds cube of x plus 6s squared d2 y3 by ds square of x plus 4s dy3 by dx of x minus 4y3 of x is equal to s cube d3 by ds cube of x epsilon minus 2 log of x plus 6s squared d2 by ds square of x epsilon minus 2 log of x plus 4s d by dx of x epsilon minus 2 log x minus 4x epsilon minus 2 log of x, which is equal to s cube d2 by ds square of minus 2x epsilon minus 3 log x plus x epsilon minus 3 plus 6x squared d by dx of minus 2x epsilon minus 3 log x plus x epsilon minus 3 plus 4x into minus 2x epsilon minus 3 log x plus x epsilon minus 3 minus 4x epsilon minus 2 log x, which is equal to s cube d by dx of 6 epsilon minus 4 log x minus 5x epsilon minus 4 plus 6x squared into 6 epsilon minus 4 log x minus 5x epsilon minus 4 minus 8x epsilon minus 2 log x plus 4x epsilon minus 2 minus 4x epsilon minus 2 into log x, which is equal to s cube into minus 24x epsilon minus 5 log x plus 6x epsilon minus 5 plus 20x epsilon minus 5 plus 36x epsilon minus 2 log x minus 30x epsilon minus 2 minus 8x epsilon minus 2 log x plus 4x epsilon minus 2 minus 4x epsilon minus 2 log x. So we have s cube d3 by 3 by dx cube of x plus 6x squared d2 by 3 by dx square of x plus 4x dy 3 by dx of x minus 4y3 of x is equal to minus 24x epsilon minus 2 log x plus 6x epsilon minus 2 plus 20x epsilon minus 2 plus 36x epsilon minus 2 log x minus 30x epsilon minus 2 minus 8x epsilon minus 2 log x plus 4x epsilon minus 2 minus 4x epsilon minus 2 log x, which is equal to 0. Which shows that y3 is a expression of the ODE 1.7 on 0 to plus infinity open interval. Further, for epsilon to 0 to plus infinity open interval, consider Wronskian of y1, y2, y3 is equal to y1, y2, y3, first derivative y1, first derivative y2, first derivative y3, second derivative y1, second derivative y2, second derivative y3, which is equal to x epsilon minus 2, x epsilon minus 2 log x, 1 minus 2 x epsilon minus 3 minus 2 x epsilon minus 3 log x plus x epsilon minus 3, 0, 6 epsilon minus 4, 6 x epsilon minus 4 log x minus 5 x epsilon minus 4, which is equal to x into minus 2 x epsilon minus 3 into 6 x epsilon minus 4 log x minus 5 x epsilon minus 4 minus 6 x epsilon minus 4 into minus 2 x exponent minus 3 log x plus x exponent minus 3 minus x exponent minus 2 into 6 x exponent minus 4 log x minus 5 x exponent minus 4 minus 6 x exponent minus 4 into x exponent minus 2 log x. So Wronskian of y1, y2, y3 is equal to minus 2 x exponent minus 2 into 6 x exponent minus 4 log x minus 5 x exponent minus 4 minus 6 x exponent minus 3 into minus 2 x exponent minus 3 log x plus x exponent minus 3 minus x exponent minus 2 into 6 x exponent minus 4 log x minus 5 x exponent minus 4 plus 6 x exponent minus 4 into x exponent minus 2 log x, which is equal to minus 12 x exponent minus 6 log x plus 10 x exponent minus 6 plus 12 x exponent minus 6 log x minus 6 x exponent minus 6 minus 6 x exponent minus 6 log x plus 5 x exponent minus 6 plus 6 x exponent minus 6 log x, which is equal to minus 12 x exponent minus 6 log x plus 10 x exponent minus 6 plus 12 x exponent minus 6 log x minus 6 x exponent minus 6 minus 6 x exponent minus 6 log x plus 5 x exponent minus 6 plus 6 x exponent minus 6 log x, which is equal to 9 x exponent minus 6, which is non-zero. So the functions y1, y2, y3 are linearly independent on 0 to plus infinity open interval. Thus y1, y2, y3 form a fundamental set of solutions for the ODE 1/7 on open interval 0 to plus infinity. So the general solution for the ODE 1/7 is y of x equals c1 y1 of x plus c2 y2 of x plus c3 y3 of x, where x belongs to 0 to plus infinity open interval and c1, c2, c3 are arbitrary constants. So y of x equals c1x plus c2x exponent minus 2 plus c3x exponent minus 2 log x, where x belongs to 0 to plus infinity open interval, c1, c2, c3 are arbitrary constants, which is required general solution of the given third order linear ODE. Well, see another exercise. Verify that the functions y1 of x is equal to 1, y2 x is equal to x, y3 x is equal to cosine x, y4 x is equal to sine x. Form a fundamental set of solutions for the ODE. d4y by dx exponent 4 plus d2y by dx square is equal to 0 on R. Formulate the general solution. Well, see solution. For exponent to 0 to plus infinity open interval, consider d4 y1 by dx exponent 4 of x plus d2 y1 by dx square of x, which is equal to d4 by dx exponent 4 of 1 plus d2 by dx square of 1, which is equal to d3 by dx cube of 0 plus d by dx of 0, which is equal to 0. Which shows that y1 is a solution of the ODE 1.8 on R. Now for exponent to R, consider d4 y2 by ds4 of x plus d2 y2 by ds square of x, which is equal to d4 by ds4 of x plus d2 by ds square of x, which is equal to d3 by ds cube of 1 plus d by dx of 1, which is equal to d2 by ds square of 0 plus 0 is equal to 0. We show that y2 is a solution of the ODE 1.8 on R. Also for exponent to R, consider d4 y cube by ds4 of x plus d2 by y cube by ds square of x, which is equal to d4 by ds4 of cosine x plus d2 by ds square of cosine x, which is equal to d3 by ds cube of minus sine x plus d by dx of minus sine x, which is equal to d2 by ds square of minus cosine x minus cosine x, which is equal to d by dx of sine x minus cosine x, which is equal to cosine x minus cosine x. So d4 y3 by ds4 of x plus d2 y3 by ds square of x is equal to 0, which shows that y3 is a solution of the ODE 1.8 on R. Also for exponent to R, consider d4 y4 by ds4 of x plus d2 y4 by ds square of x is equal to d4 by ds4 of sine x plus d2 by ds square of sine x, which is equal to d3 by ds cube of cosine x plus d by dx of cosine x, which is equal to d square by ds square of minus sine x minus sine x, which is equal to d by dx of minus cosine x minus sine x, which is equal to sine x minus sine x, which is equal to 0. We show that y4 is the solution of the ODE 1.8 on R. Now for s belong to R, consider Wronskian of y1, y2, y3, y4 is equal to y1, y2, y3, y4. First derivative y1, first derivative y2, first derivative y3, first derivative y4. Second derivative y1, second derivative y2, second derivative y3, second derivative y4. Third derivative y1, third derivative y2, third derivative y3, third derivative y4, which is equal to 1 x cosine x sin x, 0 1 minus sin x cosine x, 0 0 minus cosine x minus sin x, 0 0 sin x minus cosine x. Well, expanding this with respect to first column, we have 1 minus sin x cosine x, 0 minus cosine x minus sin x, 0 sin x minus cosine x. Expanding this with respect to first column, we have minus cosine x minus sin x minus cosine x, which is equal to cosine square x plus sin square x, which is equal to 1, which is non-zero. So the functions y1, y2, y3, y4 are linearly independent on R. Thus y1, y2, y3, y4 form a fundamental set of solutions for the ODE 1.8 on R. So the general solution for the ODE 1.8 is y(x) equals c1, y1 of x plus c2, y2x plus c3, y3 of x plus c4, y4 of x, where x belongs to R, and c1, c2, c3, c4 are arbitrary constants. So y(x) equals c1 plus c2x plus c3 cosine x plus c4 sin x, where x belongs to R, and c1, c2, c3, c4 are arbitrary constants, which is required general solution of the given fourth order linear ODE. That's it for today. Well, in the next lecture, we will find two linear independent solutions of a given second order linear ODE, provided one of the solution is given. Don't forget to share my lectures with others, and don't forget to subscribe my channel Easy Math with Dr. Nasir.